Welcome to another video. So in this video, we're going to tackle how to prove trigonometric identities. They can be challenging. So I'm going to give you some steps that is a general way to think about them. Does it work every single time? Exactly how I'm going to write this out like this? No, it doesn't. But most of the time, this will give you a good first step on how to solve or how to prove some of these trig identities. So I'm going to walk you through that. We're going to do 11 examples right now. A lot. It's going to be a long video. I know it. But it's important. And so I'm going to model my thinking. That's mostly what I'm going to be doing here is trying to teach you how to think about them. The identities themselves, I've written the ones that we use most often on the board, besides like the even and the odd and the reciprocal ones that are probably getting in your head right now. So I've written the Pythagorean identities. I'm going to go through the steps. If you watched the last video, which I hope that you did, on how to simplify some of the trigonometric functions, this is right along the same lines. So here's the thought process, and then I'm going to model my thinking on 11 examples. The first thing that we really want to look at in our trig identities is what looks like the harder side. Now, is it always the harder side? No, but it's typically the thing with more stuff on it. We work on that side, and we work on that side only if we can. So try to work on just one side. So we're going to take a look at the harder side. Whatever says, tackle that first. Then what we do is, here's some ideas. Then what we do is try to write it as one fraction if you have more than one fraction. Simplify it as you go if you can. If you can't find an identity that's apparent, so like it's just popping right at you, if you can't do that, then write everything as sines and cosines. That's a key thing. If you have some identities right there, then don't do this if you have an identity just kind of that's already there. Don't do that. It'll oftentimes simplify for you. Then use only identities that you actually know. So the ones that we've written here, don't try to make them up as you go, or things you can manipulate. So I've done that. So we're gonna do this in just a little bit. But notice that this is all the same identity. I've kind of done this a service so we don't have to go on every example and kind of redo this, but the Pythagorean identities are on the top, and then the manipulations of them, like subtracting cosine squared theta or sine squared theta, or subtracting 1 or subtracting tangent squared theta. We get two identities basically for free. So these are all stemming from these top three identities. So let's go right into it. I'm going to model my thinking. I'll tell you exactly what I'm doing. We'll talk about why I'm doing this, like I always do, and I'll refer back to these steps. So let's take a look at this. Identities are one thing equals another thing in trigonometry. That's what an identity is. We are just trying to prove it. What do you mean prove it? Basically start with one side and show that eventually it equals the other side. Now, it'd be great if we just looked at it and went, yeah, that'd be nice, but we can't. It'd be great if we could just plug in a couple values for theta and show that it works, but we can't. We have to prove this for every valid theta on the domain of these trig functions. So we have to show it for all of them. That would take us forever. And so we start with the, let's say, hard side and make it equal to the easy side, if you will. So we're going to take a look at this. What side looks harder? To me, that looks harder than that. That's just one term. This is a product. So I'm going to start with secant theta times sine theta. And I'm going to start thinking in terms of this. So this is my hard side. I'm working only on this side. Does it have fractions? I don't see any fractions. Okay, so is there an identity that's right there for me? No, I really don't see an identity right there. So I checked hard side, no fractions, no identities right there. I'm going to write everything in terms of sine and cosine. Not that. Remember, work only on one side. So secant theta, I can write that as 1 over cosine. Now, I'm not going to write equals tangent. I'm just going to work this down until it actually equals tangent. And then we'll have shown that one side equals the other and proven our identity for everything that's on the domain. Now, let's go back. All right, I'm still on the hard side. We're going to stick with that side, so that doesn't really change. But let's make this a single fraction. So I'm going to make this 1 times sine as sine theta. Over cosine theta. I've made this one fraction. Now, I've already rewritten in terms of sine and cosine, but the point here is that As soon as you do something, look for an identity that you know. So I'm looking here going, wait a minute, sine theta over cosine theta is tangent theta. As soon as you get down to what you wanted to show it. And that satisfies the proof. So we started on one side. We used some identities. We wrote everything sines and cosines. One fraction. We used a known identity, and that satisfied what you're trying to show. It showed that this side eventually equaled tangent theta, which is exactly what we stated in the beginning. That's how a proof works. This is a very good section, a very good video for you to get introduced to how to prove things. You don't just go plug in a couple numbers. You have to actually show with known mathematics that this equals that it actually works. And this is one way to go through and do that. Again, it doesn't work in this order every single time the exact same way, but it's a good series of steps, and that's why we're doing a lot of examples to build that. Let's start the next one. So secant theta minus 1, secant theta plus 1 equals tangent squared theta. I'm going to first look at this and identify what I think is the harder side. Looks like the left-hand side is harder. There's more stuff over there. Next thing I'm going to do is I'm going to look if we have more than one fraction. I don't have any fractions, so that's satisfied. I don't have anything going on there. Then I'm going to look for any identities that I have. So I don't see an identity here or here. I do see a tangent squared though, so I'm thinking tangent squared and then secants. I have an identity here with that. So I might not want to change that into sines and cosines just yet. Maybe I want to distribute this. So I have this couple factors being multiplied. Let's distribute this and see where it goes, because this is very close to an identity right here. So I'm going to choose to distribute. So secant theta times secant theta is secant squared theta. We get plus secant theta and minus secant theta. That's going to cancel, and then we get 1 times negative 1 is minus 1. So I've started hard side. I've looked at it. There's no fractions. I didn't see an identity, but I saw that we were kind of close to one, so I chose to distribute rather than write things in terms of sines and cosines. Now, what if you did write in terms of sines and cosines? Would you get the same thing? Well, you would get 1 over cosine squared theta. Now, if you saw that, you go, oh yeah, 1 over cosine squared theta is secant squared theta. And now we're down to here. So we're going to evaluate that. There's no fractions. The next thing we should do is look to see if there's an identity right here. So let's look. Hey, look, there's one right there. Secant squared theta minus 1. Secant squared theta minus 1 is tangent squared theta. And that's exactly what we were trying to prove. Identities are kind of nice because it shows you what you want to get to. So you know your goal. It's kind of like looking at the textbook in the back and going, oh, that's what I'm trying to get to. And then you figure out how to get there. I know we all do that. That's what this is really about. Start on the hard side, figure out that it makes it equal to the other side. Using these ideas that I'm giving you. So tangent squared theta does in fact equal tangent squared theta. And that satisfies our proof. Man, how about the next one? These are getting a little bit more complicated. Cosine theta times tangent theta plus cotangent theta equals cosecant theta. I think there's no argument. That's the hard side. So let's start there. We're going to only work on that side. Let's see how this works out for us. We start by seeing if there's more than one fraction and trying to combine them. Now, I don't have more than one fraction. I'm going to look for any identities or things that are close to identities. This was very close to an identity. I saw it because I was trying to get tangent squared. That's what led me down this thought process of distribute rather than go to sines and cosines. Here, I'm not seeing any identities that are coming up here. I don't see any squares. I'm not seeing anything that looks similar to this stuff over here. So I'm probably going to write this in sines and cosines. There's no fractions, there's no squares, there's no other identities. Let's go sines and cosines on this. So that cosine, it looks good, but this should be sine theta over cosine theta. This should be cosine theta over sine theta. And I'm only working on one side. So I've done that. Now we have a choice here. Could you get one denominator and make that one fraction? You could, but I do notice that I can simplify this. So that's why I said these don't have to go in a hard and fast order. We're always looking to see if we can simplify things as we go. We're always looking at, do I have an identity that's close? Do I have a simplification that's close? Instead of making this one fraction right now, I'm going to choose to multiply and simplify as we go. So I'm going to distribute this. So cosine theta times sine theta over cosine theta, that cosine is going to cancel. We're going to get sine theta. But here I'm going to get cosine squared theta over sine theta. What if you would have got one fraction here multiplied by sine over sine, cosine over cosine, and then distributed? Would you do the same thing? Yes, you absolutely would. It's actually not that big of a difference. You'd get a common denominator of sine theta, cosine theta. Your cosines would still cancel, and you'd get exactly what we're going to end up with here in just a minute. You see, at this point, I have two fractions. This is over 1. This is cosine squared theta over sine theta. I need to make this one fraction. So I've looked at it and said, that's the hard side. I didn't see an identity. I didn't see a simplification, so I distributed it. So I changed it into sines and cosines. I didn't see a clear identity here, so I distributed. I saw cancellation there. That's why we did that. Now I have two fractions. I'm going to try to make that one fraction because I don't really see a great identity that's leading me onto that. That what we're trying to get to. So I'm going to make this into one fraction. Because this is over 1, my common denominator is sine theta. I'm going to multiply that on the left-hand side over here. So when we do it, we get this sine squared theta over sine theta. Plus cosine squared theta over sine theta. Oh, look, we got a common denominator. We can now make one fraction. And you're going to see exactly why we do that. Why this is here, get a single fraction, is because a lot of times when we do that, things cancel. And also, we get some identities just pop right out of this. So we're going to get sine squared theta plus cosine squared theta. Over sine theta. Another thing that I hope that you're seeing me model is this idea of I'm always checking, is there something I can simplify? Is there an identity that's popping out at me? What that means is that it's very apparent, that's readily available, that's on the board right now. So I did that from here. I looked, is there identity? No, not really. Are we close to an identity? Yes, for here, I'm going to distribute that. It's very close. Here, not so much, change sines and cosines. I see a simplification, so I notice that. I'm going to distribute and simplify. Could you have made one fraction? Yes, and it would work out just as well. After that, I'm looking for an identity. I don't really see one very well, so I'm going to make one fraction. Okay, we made one fraction. Let's look for identity. I see one right here. Sine squared theta plus cosine squared theta is 1. So instead of doing anything else, like simplifying this some other way, we're going to use identities right when they come up. So sine squared theta plus cosine squared theta is 1. That's going to give us 1 over sine theta. Now remember, we're trying to get here. So let's think about 1 over sine theta. 1 over sine theta is cosecant theta. So we did all this work and got down to cosecant theta. Cosecant theta does equal cosecant theta. We've now proven this identity. I hope that's making sense. I hope that you're seeing the thought process. We have a lot more to do, but right now the ideas should be sort of building in your head on how to at least approach these identities. Let's keep right on going. So we've got the sine theta cosecant theta minus cosine squared theta equals sine squared theta. Start with the harder side. This is obviously the harder side. That's just one term over there. So we're going to take a look at this under the lens of, do we have more than one fractions? Do we have identities that are just popping right out of us, or do we need to write everything in sines and cosines? So I don't have any fractions at all. I'm looking at this. That looks really close to an identity. So it looks It has something to do with this over here probably, but this doesn't. And so I'm going to try to write everything in terms of sines and cosines and see what happens. So sine theta, cosecant theta. But cosecant theta is 1 over sine theta. So we're using that reciprocal identity. So I'm working on just one side. Now, let's make one fraction, or just realize that sine theta times 1 over sine theta, that's going to cancel. You're going to get 1. So I've simplified an obvious simplification there, and now I'm going to reevaluate. This has no fractions. Everything's in terms of sines and cosines. Do I have an obvious identity? Well, 1 minus cosine squared theta, that's one of the ways that we can represent the Pythagorean identity right here. So 1 minus cosine squared theta, that is sine squared theta. And we've got down to exactly what we wanted to prove. So we've shown that this side is sine squared theta theta equals sine squared theta on its domain. And we're done. That's exactly proven identities. Let's do the next one. So next one's, man, this is a really good example for why we don't always just write things in terms of sines and cosines right off the bat. So when we look at it and go 1 minus cosine squared theta times 1 plus cotangent squared theta equals 1, remember the ideas. The ideas are, if you have one fraction, yeah, you're probably going to, if you have more than one fraction, yeah, you're probably going to make this in terms of one fraction. But we're always looking for, can I simplify it? What's going to let me simplify it easily? And do I have any identities that are right there already? Because if I do, I don't want to be writing things in terms of sines and cosines if they're already in an identity that I can use. So when we take a look at 1 minus cosine squared theta, we just did that. 1 minus cosine squared theta is an obvious identity. Well, maybe it's not obvious to get used to. It's maybe a bad thing to say. Sorry. But it's an identity that is known. So 1 minus cosine squared theta is sine squared theta. That's great. Why change that if it's already an identity we want to use? Let's make that into sine squared theta. One plus cotangent squared theta. Again, we're not going to be writing things in terms of sines and cosines if we have an identity already there. 1 plus cotangent squared theta, or cotangent squared theta plus 1, is cosecant squared theta. So we started with the hard side. We looked for the one fraction thing. We didn't have any fractions. We thought about maybe doing sines and cosines, but we want to check for simplification and for identities that are already known in there before we do that. And there's 2 identities here and here that were just right on the board for us. That's great. Now we reevaluate. Can I simplify that? Not that it looks like. Is there a known identity that works with this? Not that I can tell. Now is when we write everything in terms of sines and cosines. So sine squared theta times cosecant theta is 1 over sine theta. So cosecant squared theta is 1 over sine squared theta. And now we reevaluate. We have more than one fraction. Could you write this as one fraction? Yeah, you would get sine squared theta over sine squared theta. That's going to simplify and give you 1. 1 does equal 1. We worked on one side, got it down to exactly what it said that it should equal. That's proven that identity for us. Okay, so secant to the 4th theta minus secant squared theta equals tangent to the 4th theta plus tangent squared theta. Don't you wish you could just go, sure, nailed it. I believe you. They're all worked anyway, so why do I need to prove it? First, because it's good for you. And it doesn't feel good for you sometimes. But secondly, because it's important to understand how these proofs work, important to be able to work with them, and to give ourselves more identities. So understand that every time we prove something, you can now use that. So if you ever see this again, anywhere in your math, you know that that is true. So you'd say, oh yeah, okay, you're not even given that, you know that that's going to equal 1 if you have this list of identities. And you can do that. You can develop your own identities like we're doing right here. So let's start with the hard side. What's the hard side? They look probably equally difficult. Secants look a little more difficult than tangents to me, so I'm going to start there. So I'm going to work on my left-hand side. I'm looking at that thinking, is there an identity that's right up there? There's one that's close. I like that secant squared theta. I don't like the secant to the fourth theta. So instead of writing everything in terms of sines and cosines, because I'm thinking this is probably close to some identity, I'm going to factor. I don't like the fourth power anyway. I'm going to factor out a secant squared theta. That would be a little more simple. So let's simplify that by factoring. So factoring out secant squared theta, we get secant squared theta times secant squared theta minus 1. You can see by distribution that's true. It's just basically like having x to the fourth minus x squared. You're factoring a GCF. Now let's reevaluate. Do we see an identity that's right up there, something we can simplify? Secant squared theta minus 1 is right there. That is equal to tangent squared theta. So let's use that right when we see it. Don't do sines and cosines if you have an identity that's right there for you. Now, we have the secant squared theta times tangent squared theta, and this is one of those times that you want to keep in mind what you're going towards. You're trying to get to tangent to the fourth theta times tangent squared theta. This is one of the times where writing things in terms of like sines and cosines probably wouldn't be that beneficial because I already have a piece of that. I have a tangent squared theta. What's the thing that I don't have in terms of tangent? That one. So maybe we use this and write this in terms of tangent. So let's use the identity to change this thing. So let's see, secant squared theta is tangent squared theta plus 1. So I've kept on one side. I've seen that something was close to an identity, so I factored. I used the identity I thought. I got that, and now I'm checking. This is pretty close to this. I don't want to do sines and cosines because I already have a piece of that. This is not close to that. Let's change that one with a known identity. So we've done that. Now we're so close, but keep in mind what we're trying to get to. We're almost there. Let's distribute this. And that satisfies the identity that we just proved. So is it always exactly like this every time? No, it's a good set of steps, but we gotta be critical thinkers. We gotta be thinking about it. The ideas are, this works most of the time. The ideas are, well, simplify if you can. If you have a known identity that's gonna help you, use it right when you see it. Also keep in mind what our goal is. Your goal is to try to get this thing over here. So sometimes writing things in terms of sines and cosines, not such a great idea. If you're completely stuck, then yes, that's a good way to go. So I hope it's making sense. I hope that I'm making it very clear for you. We're going to step it up and do 5 what I would consider really difficult proofs. Let's go on to this example. We're gonna prove this identity, and it's going to use something that looks like a trick, and frankly, it is kind of a trick, but it's thinking really smartly about what we want and what we have. So 3 sine squared theta plus 4 cosine squared theta equals 3 plus cosine squared theta. I want you to look at this side, what I would consider the harder side, and take a look how this looks a whole lot like this one. Looks very, very similar, but there's a 3 here and a 4 there. If this was a 3, couldn't you factor the 3 out from both terms? Yeah, and then that would be 1, but that's not a 3, that's a 4. Well, can I write it a little bit differently? Instead of having 4 cosine squared theta, we can do things that are, man, it's a really kind of a smart move here, but we can do things that let us write this as like 3 cosine theta, it's cosine squared theta plus 1 cosine squared theta. So check this out. If this is really close to an identity that we want, try to make it fit. It's already, in terms of sines and cosines, that wouldn't help us. I don't see an identity that's just right out there and I can't factor it the way it is. Write it as something we can factor. This is still 3 sine squared theta plus 3 cosine squared theta cosine squared theta. That's still 4 cosine squared theta. But it's made it so that this piece you can factor. If you look at just that piece and factor out the 3, well then now that's a good identity. So sine squared theta plus cosine squared theta, that's one of our Pythagorean identities. That's 1. So this is 3 times 1. And that's exactly what we're trying to prove. So I hope that makes sense. I mean, it looks like a trick. It kind of is a trick. But it's also understanding that if you're very close to an identity, this is what we saw in a few previous examples, is make that identity work somehow. Don't change the identity. That it's there. It's right there. Just make it work. Structure it so that you can structure this so that the identity can pop out at you. Well, that looks a little crazy. So sine squared of negative theta minus cosine squared of negative theta over sine negative theta minus cosine negative theta equals cosine theta minus sine theta. When you see those negative angles, those negative, whatever the argument of your trig function are, and that's negative, use an identity. Use the even and odd identities. Remember, the sine's an odd function and cosine's an even function. It means they're changeable. You can change that. And so we're going to do it. We're going to structure it a little bit differently. This is obviously the hard side. It's already one fraction. But we're going to structure it a little bit differently so we recognize what's going on. So sine squared means sine of whatever that angle is all to the second power. This really means this. This is sine of negative theta quantity squared. Same thing as that means. Sine squared negative theta means this thing right here. All over. Let's start using the even and odd identities. So sine of negative theta is the same thing as negative sine theta. Opposite inputs, opposite outputs for odd functions. No, we're not just pulling the negative out front. That doesn't happen with trig functions. You need identities. You can't just make it up as you go. We'd love to, but we can't. Sine's odd. It's an odd function. So that means that if I plug in a negative and a positive with the same absolute value angle, you're going to get opposite results. And that's exactly what we've shown here. Cosine's even. So cosine says opposite angles equal outputs, which means cosine of negative theta is the same thing as cosine positive theta. And we're going to use that here too. So sine of negative theta is equal to negative sine theta. That's an odd function. Cosine of negative theta is equal to cosine positive theta, even function. I also might factor out my negative. I don't like that negative there, so let's do that. So I've taken and said, that's an odd function. Okay, that's going to be a negative. That's an even function. It's going to be a positive. I have the power twos. I have the minus. I factor this out because we really don't like seeing both those minuses down there. And now we're going to go ahead and evaluate this. Negative sine theta squared. What would happen with that? Well, that would be, let's see, negative 1 squared. That's what that is. Negative 1 squared would be positive 1. Sine squared would be sine squared theta. Minus cosine squared theta. All over negative sine theta plus cosine theta. Man, that's really close to an identity, but it's not one. It's not an identity. Maybe what we can do is run this negative through there and see what happens. So I have everything on one fraction. I have sines and cosines, but I'm not seeing a clear identity. I also don't like that negative. So I'm going to make this negative sine squared theta plus cosine squared theta. Now it looks like we're kind of in the same position. I don't see an identity popping out at me. I've taken care of that negative. It looks about as simplified as I can make it. I don't see an identity that's like, do this right now. So maybe we try something else. Try something like, can you factor it? Well, if everything's in terms of sines and cosines and I have this all in one fraction and I don't see an identity, you need some other algebra. Try to factor it. I can't factor the denominator, but the numerator, that's a difference of squares. That can be written, if you had like x squared minus y squared, you'd write x minus y and x plus y. Well, we have the same sort of situation. Let's write cosine theta minus sine theta, cosine theta plus sine theta. Being a difference of squares, it's nice, that'll work for us. We also might have noticed a little bit that that's what our denominator suggests. So sometimes we can sort of cheat a little bit and look at what we're trying to get, what we have currently, and what would it take to simplify that. So if I'm trying to get this, and I have that thing, and I have this that I don't know what to do with, try to factor it. Maybe it's going to cancel and give you exactly what you want. And that's exactly what happens. So when we factor this as a difference of squares, we simplify the denominator that we have. That's why we chose to factor that negative so that it would be more apparent what happens. So we're putting this in correct form so that it's easier later. So from the top, use your even and odds, make it simpler. Simplify as much as you can. Get down to something that's nice to work with. Negatives and denominators are not really good things. Move it. Structure this so that it's easier to look at. Positives first, minus others, and then try to evaluate. Everything sines and cosines, one fraction, but I'm looking at what I need, what I have, and letting that determine, because there's no identities that are right out here for us, that, man, I can factor that by difference of squares, simplify what I don't want, and this gives me exactly what I did. So this is cosine theta minus sine theta. And we proved that the left side actually equals the right side. That proves our identity. Let's go ahead and tackle another one. So 1 minus cotangent squared theta over 1 plus cotangent squared theta plus 2 cosine squared theta equals 1. That's a lot. That's obviously the harder side. Let's start with that. Now, before we get going, look for any identities that are apparent, but don't get tripped up. Don't try to make them up on your own. This is a great one. So 1 plus, cotangent squared theta plus 1 or 1 plus cotangent squared theta. That does equal cosecant squared theta. But this is nowhere on our list. In fact, that's going to cause us a lot of problems on this particular problem because that's not an identity. Even though it really looks close, it's not one. It's not one of those things. So what we're going to do is we're going to use the identities that are right there on the board for us right now. We're going to change that into cosecant squared theta. Now we're working just on the left-hand side, so we're taking a look at it going, now I don't see any other identities. I don't see anything that's very nice to simplify, nothing that's at least popping out to me. So maybe now's the time where I make one fraction out of this. That's one of the ideas here, is to get everything on one fraction, see what happens. So let's do that. Because I'd have to multiply by cosecant squared theta, we're going to get 2 cosine squared theta times cosecant squared theta all over cosecant squared theta. Let's put that on one fraction. That's what we did that for, is to get a common denominator so that we could combine this. Well, that doesn't look very appealing at all. In fact, I don't even see an identity yet. Still isn't 1. This isn't 1. But what I do see is this one's somewhat close. We saw that from the beginning. It's pretty close. This is not. In fact, this has a cosine and something over sine. So this right here, maybe I work on this piece, just this piece, and try to get this written in terms of sines and cosines. If cosecant theta is 1 over sine theta, then cosecant squared theta is 1 over sine squared theta. And we're going to make that little piece one fraction. Wait a minute. Cosine theta over sine theta is cotangent theta. So that would be cotangent squared theta. So this whole thing becomes 2 cotangent squared theta. That's something we can simplify. So don't change the sines and cosines now, not when you have a combining like terms idea. Let's go ahead and do that. So we saw this is an identity. This is really close. So we're going to use identity. We saw 2 fractions, make them 1 fraction. Okay, simplify whatever we can. Well, you notice that this is pretty close to an identity. I'm going to leave that one. That looks really close over here. This looks like garbage. Fix this one first. So sines and cosines, let us do that. That's cotangent squared. So I did 2 cotangent squared theta. Now let's combine some like terms. This is negative cotangent squared theta plus 2 cotangent squared theta. That's plus 1 cotangent squared theta. So this would be 1 combine like terms plus cotangent squared theta. Oh, this is great news, because now instead of making everything sines and cosines, our first step before we do that is use identities that are already there. So 1 plus cotangent squared theta, that is exactly what we want to see. That's cosecant squared theta. And cosecant squared theta over cosecant squared theta is 1. So we worked on the left-hand side all the way down to here, and we got 1. That's exactly what we were trying to show. 1 does equal 1, and so this satisfies and proves our identity. I really hope this is making sense for you. I hope that you're seeing the logic, our ability to change with these problems. That it's not just a hard and fast, this is what you do every single time. We really have to think about it. They're multifaceted. There's a lot of things going on here. And that's what makes them very challenging. I hope I've given you a good outline that you're able to use for this. We only have like 2 more examples that are, in my opinion, probably the most difficult. The last one's the most difficult one that we can go through. It's going to be a lot to it, but I hope that you're seeing the structure. I'm really trying to explain my thinking so that you can pattern yours on that. All right, let's get right to it. So we've got a nasty problem. It's an identity, and it is going to be true. So we're going to show that this equals 4 tangent theta secant theta. Keep that in mind. We're trying to get tangents and secants out of this. We are given everything in terms of sine. We're also given things on 2 fractions. So when we take a look at it, I'm going to work on the harder side. I'm going to look at this thinking, I don't see any identities that are just popping right out at me, but I do have 2 fractions. Let's start with that. Everything's already sines and cosines. Let's make this into 1 fraction. 1 fraction means you need a common denominator. So I'm going to multiply this by 1 plus sine theta and this by 1 minus sine theta. It's going to give us 1 plus sine theta quantity squared minus 1 minus sine theta quantity squared. So let's do that. 1 plus sine theta times 1 plus sine theta is 1 plus sine theta squared. Likewise over here, but on the denominator we get 1 plus sine theta times 1 minus sine theta. And we're going to go ahead and distribute that. So 1 minus sine theta plus sine theta, that's canceled, and then minus sine squared theta. So we're going to end up with 1 minus sine squared theta. Now that's a really good thing because this is an identity that says that we're going to have cosine squared theta on our denominator. The problem is our numerator. That looks really crazy. Man, what to do? Well, we can't just cancel these things out, but maybe if we distribute this, some of the things will actually simplify. So let's go ahead and do it. We'd have 1 minus 2 sine theta, 1 plus 2 sine theta, and then plus sine squared theta. Over here, we'll get 1 minus 2 sine theta plus sine squared theta. So we're distributing this as 1 plus sine theta times 1 plus sine theta. You can do it off to the side if you want to, but ultimately what we get is 1 plus 2 sine theta plus sine squared theta. That's this. So this came from our first distribution minus, oh my gosh, it's really important to make sure that you have parentheses around what you're going to distribute here because you have that minus. It's going to change all of your signs. So this would be 1 minus sine theta times another 1 minus sine theta. That's going to be 1 minus 2 sine theta. And then plus sine squared theta. You're going to see right now why it's so important to have this parentheses. Hopefully you're with me. Hopefully you're understanding the distribution here. I did see an identity. We're going to use that right now. That is going to be cosine squared theta. But I didn't see an identity here or here. I had to distribute that. There's nothing else we could do. There are already sines and cosines. Now that we have distributed that, our signs are all good. We have parentheses here. Let's go ahead and run this through and change all of our signs. I'm also going to make this cosine squared theta. So I'm using identities that I know that are already popping up. Denominator looks really good. It's as simple as we can make it. It's the numerator that's sort of messing with us. So let's go ahead and write this out. None of the signs here are going to change. All of the signs here. Yeah, can we combine anything? Can we simplify it? We're always thinking that. We're thinking, do I have any identities that are right there? Can I simplify? What's going to take to simplify? For us, what it took was we need one fraction, common denominator. Then we simplify what we get there. Okay. Then we have an identity that's known. Use it. We can't simplify any of this stuff. Distribute that. Combine some like terms. Now simplify it to make our numerator look a little bit better. So we're going to say 1 minus 1 are gone. We'd have a 2 sine theta and a 2 sine theta. That's 4 sine theta. My sine squared and my other sine squared, one's plus, one's minus, those are gone. We're going to get 4 sine theta, not sine squared, we're not multiplying, we're adding 4 sine theta over cosine squared theta. This is as simple as you can make it. So there's no other simplifying besides what we've done. But it's not what we want. This is why I said that you got to really focus on where you're trying to get to sometimes on this. We're trying to get to a tangent and a secant. Now, how in the world are you going to do that? Well, if we have everything in terms of sines and cosines, let's try to make this a tangent and a secant. We have sine over cosine squared. Maybe if we split that cosine squared and think about it as sine over cosine times cosine, or more specifically, sine times 1 over cosine times cosine. Because this is tangent and this is secant. The only reason I knew why to do that was because of what we're trying to get. So I knew we were trying to get a tangent. Let's make that. It's sine over cosine. We also need a secant. That's 1 over cosine. And now that we can structure that, this proves our identity. And that's exactly what we wanted. So hopefully that's making sense. Sometimes we have to have an eye on what we're trying to get to in order to structure what we're going to do next. A lot of this was make one fraction simplify, use identities that show up, simplify some more, and then when you get stuck, if you're already in terms of sines and cosines, if you're not, move into sines and cosines. If you're already there, look at what you need to get to, and sometimes that'll help you. So we get one more, and then we're done. All right, this is going to take a lot of work, and I'm going to go pretty quickly through it. I'm going to show you I hate using the word trick, a manipulation trick, to make this nicer and why I'm using it and where in the world I would see it. There's going to be a lot of combined like terms, a lot of little identities that we see in here. Let's get right to it. So let's start on the harder side. I'm just going to model my thinking, kind of show you, it's kind of a fun problem in that it's very challenging, like a puzzle, but it can be extremely difficult if you don't see a couple things about this. Number one, when you have stuff that looks really similar, that's off by a sign, like this one is, try this. Try factoring so that you make a couple pieces look the same. Why? Because what we're going to do here is multiply in such a way to create a difference of squares look on the denominator so that stuff cancels out. So right now this looks very, very close. You go, well, what would I want? I would want this idea of 2 terms. Why 2 terms? So that we can do a difference of squares sort of multiplication. So this 3 terms is nonsense. I mean, you can't do much with this. But if I structure this as secant theta minus 1 and secant theta minus 1 and treat that like one term, then I have stuff that's very similar. In fact, if I were to take one of these and multiply it by the other, I would get this difference of squares look. So what we're going to choose to do is take the numerator and multiply something over itself so that I get a difference of squares on the denominator. The denominators are typically harder to work with. So I'm going to multiply by that. So we're going to take this thing and multiply it here and here. Notice, you can multiply whatever you want as long as you multiply it to the numerator and the denominator. So we're going to do it. Just a little side note, it doesn't have to be the numerator that you multiply. It can be, don't do that. It can be whatever you want. So even if the numerator wasn't there, you could say, I want to multiply by this thing, except with that a plus. It looks a lot like a conjugate. Do you remember that you can multiply by a conjugate of things? That's practically what we're doing here so that we create a difference of squares idea. Now the numerator is just this quantity squared. I'm going to choose to distribute right now, but it's just multiplying through. What we really did was look at your denominator, try to create this idea of a difference of squares multiplication that you have. You can multiply whatever you want, but it took the idea of having 2 terms to do that. So we said 3 terms, no. Let's structure it so that we have 2 terms. Your denominator stinks. Let's multiply to get rid of this idea of Something that you can't factor, we want some squares in there that are factorable, something nicer, so we're going to do that. Numerator just sort of plays along here, just so happens that it's going to be squared because it is that idea of a conjugate if you look at this in terms of two terms. So let's go ahead and multiply through. We're going to get tangent squared plus, let's see, tangent times secant theta minus 1, tangent times secant theta minus 1, so that's 2. And then plus secant theta minus 1 squared. On the denominator, we chose to do this idea of a conjugate. One term, two terms, one term, two terms with a different sign in the middle is a conjugate idea, so that we get our middle terms canceling. That gives us tangent squared theta minus secant theta minus 1 squared. We're going to have a whole lot of distributing to do here. So we've taken and just distributed this here and distributed this here, but noticing that I'm subtracting that, my signs are going to change. I'm also taking a look at this, looking for any identities, anything I can combine. I see a tangent squared theta plus 1. Tangent squared theta plus 1 is secant squared theta. So I'm going to take this and that, and I'm going to call it secant squared theta. Here I'm going to change signs. So I've combined. This is secant squared theta. I've got it. I have the same thing here, same thing here, same thing here. I've gone ahead and changed my signs by subtracting term by term. Now I'm going to combine some like terms. I see a secant squared and a secant squared. That's 2 secant squared theta. I'm also noticing this is really, really, really close to this. It's super close, but it's backwards. So if I thought about this, tangent squared theta minus secant squared theta, if I did tangent squared theta minus secant squared theta, I'd get -1. So we can use that. Combine like terms, I get 2 secant theta minus 2. I'm going to restructure this so I can factor. And so we're going to factor this. We're going to factor a 2 here. We're going to factor a 2 secant theta from the numerator. And we see that we can do one of two things. We have 1, 2 huge terms, both of which have secant theta minus 1. You could factor that out, but this also has that. So use some math here and simplify all of them. So divide denominator and numerator all by secant theta minus 1. Do the same thing again. We can divide everything by 2. And that satisfies our identity and proves it. I hope it makes sense. We did a ton of factoring and a ton of simplification, not a whole lot of identities. I hope I've given you a set of steps that you can use to structure your thinking for identities. Thanks for watching. Have a great day.